My name is Kara, and this is my Physics 2211 Lab 1 on constant velocity. Here's the table of contents. We'll discuss the introduction, analysis of the can's motion, construction of the computational model, the observed versus predicted graph, and what ifs/what does it mean discussion questions. The purpose of the lab is to observe and analyze the motion of an object moving at constant speed using the tracker device to compare it to a computational model using GlowScript. These two datasets will then be graphically compared, giving the predicted versus observed graph. My prediction is that they should look similar because the computational model uses physics equations to predict the motion based on observed values. Here are some key concepts and equations to keep in mind. First, we have Newton's first law. An object in motion remains in motion, or an object at rest remains in rest at a constant velocity unless acted on by an external force. This is relevant because the system is not being acted on by an external force, so the system stays at a constant speed. Then we have Newton's second law. Net force is equal to mass times acceleration. We can use this because there is not a change in velocity, no acceleration, so therefore there is no net force acting on the system. Then we have the velocity update formula, which is derived from Newton's second law, and this formula shows why the velocity stays the same, because there's no net force acting on the system. The net force is 0, so the velocity is constant. And then finally, the position update formula. This estimates the next position based on the average velocity in the time intervals. Here are some models to help visualize the net force. I established that the system is the soda can and the surrounding is everything else. So initially we have the normal force and gravity, which cancel each other out, leaving the applied force to the soda can moving in the positive x direction. So the net force is in the positive x direction initially. And then during constant velocity, the only two forces acting on it are the normal and gravitational force, which cancel each other out, so the net force is 0 during the constant velocity. This is also assuming that we are ignoring the force of friction and air resistance on the object. Here's the tracker analysis of the soda can's motion, which measures the position of the soda can as a function of time. The soda can moves from left to right, so it moves in the positive x direction, which creates a positive slope of position versus time. Here's the tracker analysis data, which I used to help build the computational model. The approximate diameter of the soda can was 0.064 meters, and the mass was around 0.132 kilograms. I also recorded the initial start time of the can's rolling and the final time after it reached a meter, and then the can's initial position. The work on the right is what I used to find the can's initial velocity using the change in position divided by the change in time. I got the initial velocity to be the vector 0.19200 meters per second. Here's my GlowScript code, which I used to find the computational model of the constant velocity. Here I entered the mass of my soda can, which I found on the previous slide, as well as the initial position and velocity vectors, which I also found on the previous slide. Here's another section of my code where iterations were done by using a while loop, where I set the time to be less than the final time when the can reaches a meter. Here you can see I also had to insert the position and velocity update formulas into code, and you can see those on line 59 and 61. Here are the GlowScript results after you run the code, and you can see the position versus time graph as well as the velocity versus time graph. There's also a visual model it produced that shows a ball rather than a can, but moving in the positive x direction. Here's the position versus time graph, which compares both the observed and predictive graphs. Here you can see the tracker analysis is the observed and the computational modeling is the predicted. Here are some possible errors in the experiment. One was that the camera angle was off. It was filmed from a higher angle and not far enough away for the soda can to be perfectly aligned with the camera. Another one is that we assumed there were no forces acting on the system, for example, friction and air resistance. And then also just human error with using the tracker modeling and not pushing the system at a constant velocity. And finally, the discussion questions. What if? So how would my results change if I were to flip the axis? So the data would be reflected across the x-axis, so the direction of the position and velocity vectors would be flipped, so from positive to negative. However, the magnitude will stay the same, so it would be the same except for negative. And then, is it possible to know how many forces were added together to give a zero net force? No, because we know that the normal force and the gravitational force cancel out, and it's more difficult to incorporate other forces such as friction and air resistance because they act in the opposite direction of the motion, but there's also the potential of other forces acting on the ball. So no, we cannot tell.